In this video, I'm going to talk about something which has fascinated me for years and is part of the HSC physics course. It's in the last module, module 8, from the universe to the atom, and it's on the quantum mechanical nature of the atom. It's just something that really blows me away. It just shows how progress in science works. It's really just building upon others' work, something absolutely amazing. I'll begin with Bohr's atomic model. So every high school textbook, science textbook around the world pretty much contains pictures of atoms, representations of atoms using this model. So it was actually proposed in 1913 by a Danish physicist named Niels Bohr. A very interesting figure. He was a soccer player, apparently, as well, in the 1900s. And he actually further refined Rutherford's model of 1911. So 1911, the New Zealand-born British physicist Ernest Rutherford developed an atomic model which stated that atoms contain this really dense, very small but dense nucleus with a positive charge, overall positive charge, and there are these negatively charged particles called electrons just swarming around it. Okay, it was great in the sense that the model had a nucleus, had something at the center, and it had negative charges around it. What it didn't explain, however, was the arrangement of those negative particles, those electrons going around the nucleus. It couldn't also explain the stability of the atom, what kept it stable, because according to classical physics, classical electromagnetism, a moving charge, which in this case an electron, a moving charge should emit electromagnetic radiation. Okay, it loses energy. Anything that's charged and is moving will emit energy. It'll lose energy. And so by that token, the electron, according to calculations in classical physics, the electrons should just spiral into the nucleus and the atom will collapse, which is a big problem. And this model is actually wrong. We now know. And of course, in everyday life, this isn't the case. Okay, we know that atoms exist, they're stable. So Bohr wanted to further refine this model. And what he did was he based his work off Planck, Max Planck, also known as the father of quantum physics. He kickstarted the quantum physics revolution in 1900. And he proposed that energy comes in chunks, in discrete chunks called quanta. Okay. In other words, energy, so any form of radiation, electromagnetic radiation, like X-rays, etc., comes in discrete chunks, and energy is quantized. It's a fancy way of saying that energy comes in discrete chunks. So you can think of a light, let's say a light ray coming in as such. Okay, light comes in. We know that light's made of light rays, made of lines. If you zoom into those lines, okay, depending on what experiment you do, you can actually detect little chunks. Okay, and these chunks are called quanta. Quanta is plural for quantum. Quantum is singular. There are little chunks, also known as photons. Okay, light's made of photons. So he based his work off Planck and Rutherford's model in 1911. So Bohr's model is also known as a semi-classical model because it incorporates ideas from both classical physics and quantum physics. And Bohr came up with 4 postulates. And this is what students, physics HSC students need to know. 4 postulates or 4 principles, 4 ideas. First one is that electrons must move in circular orbits around the atom, okay, around the nucleus, due to electrostatic attraction between the electron and proton. So here's, let's say, a very simple atom. That's a proton. So the simplest atom that Bohr worked on was hydrogen. Okay, hydrogen's got 1 proton, 1 electron. And Bohr's reasoning was that electrons move in circular orbits and they're held in place by the attraction with the proton. So there's an electrostatic force there of attraction. That's a hydrogen atom here. That's the first postulate. His second postulate was that electrons can only exist in specific locations around a nucleus. Okay, they're called shells or energy levels. Okay, and this is called electron configuration. Okay, so here's, let's say, a nucleus. Let's suppose we've got helium here, 2 protons, 2 neutrons. In the first shell around the nucleus, only 2 electrons can fit. Okay, in the second shell, only 8 electrons, and so on and so forth. Okay, so there's a maximum number of electrons that can fit in each shell. That's his second postulate. His third postulate is that to move between energy levels, electrons either absorb or emit electromagnetic radiation, aka light. So let me draw here a proton, back to the hydrogen atom. What does this mean? Well, in order for an electron in the first energy level to go into the next one, the highest one up, so that's energy level 1 here, energy level 2, it must absorb light. So let's say you zap an atom with a laser. Okay, an electron in the lowest energy level, also known as the ground level, will jump up. Now, it's not energetically favorable for an electron to stay in the second energy level. So it jumps back down to the first one, and in doing so, it releases a photon, a light ray. And according to Max Planck, so that the change in energy given by the symbol delta is simply given by the energy of the final state, the energy of the final energy level that the electron is in, minus the energy of the initial energy state, energy level. That's given by HF according to Planck. Okay, in other words, light is quantized, comes in discrete chunks. Okay, that's a photon here. Okay, that's the energy of a photon. H is just a number, it's a constant. It's called Planck's constant in honor of Max Planck. It's a very small number, very small. It makes sense because quantum physics happens at a very small scale. 6.626 times 10 to the minus 34 joule seconds. And F is just the frequency of the photon, frequency of light given in hertz. Okay, so electrons can only jump between levels if they absorb or emit energy. And Bohr's last postulate is known as the quantization of angular momentum. What's angular momentum mean? Let me demystify this for you. Consider a proton, hydrogen atom, an electron. Okay, we know from basic physics momentum. What's momentum? It's a measure of how, basically, the best way I can define it's a measure of how hard it is to stop a moving object. Okay, momentum is given the symbol P. It's just the mass of an object times its velocity. Okay, so a moving bullet is harder to stop than, let's say, a tennis ball. Okay, because it's got more momentum, it's got more velocity. It's traveling really fast. That's momentum from everyday life. Okay, and this formula applies to for objects in linear motion. Linear means they're traveling in a straight line. So a bullet travels in a straight line in midair. A tennis ball, when hit, travels in a straight line as well. There's a thing, it's called angular momentum, and this only applies to objects that are moving in circular motion. So an electron moving around a proton, it's doing that via circular motion, okay? Think of a car going around a roundabout, same story. So the electron has a mass m, and let's say it's some distance r away from the proton, traveling away at some velocity v. So angular momentum is given the symbol L. It's just the mass and velocity, as was the case in the linear momentum case, times the radius r. And Bohr said that this postulate is actually linked to the second postulate that he proposed over here. Okay, that electrons can only be certain distances away from the nucleus. And since the radii of electron shells are quantized, then so must their angular momentum as well. So in other words, so I'm going to use the symbol letter N. Since let's say N's an integer, so in other words, electrons can only be an integer number distance away from the nucleus. Okay, so N's a whole number. You can't be 1.5, let's say, 1.5 units away. It can only be 1, 2, 3, etc. And r is the radius here. So if that's the case, then that implies that the angular momentum must be quantized too. And Bohr took this further, and he used the result from a paper written by John W. Nicholson in 1911 on atomic structure. And Nicholson is actually known for quantizing angular momentum in units of h over 2 pi. So Nicholson actually used Planck's constant. 2 pi would come from the fact that you're using a circle, in this case, just for circular motion. So Bohr stated that angular momentum, mvr, is equal to nh over 2 pi. Okay, it's quantized.